this video, we're going to talk a little bit about limits of functions in general, taking a real lens towards computing the limits of particular functions of importance to us at infinity. And near the end of this collection of slides, we'll really be looking mostly at the limit of rational or algebraic functions as we approach infinity. Now, to start this out, when we're in a calculus class, we have four main types of functions that we really like to consider. The first word that I used was an algebraic function. I could really use something like a polynomial function here. That's the starting grounds for my family of algebraic functions, but I want to be a little bit more broadly encompassing than that. So I do want to think about things like polynomials, x squared minus 1, but I also want to think about maybe taking the square root of a polynomial, or looking at what's called a rational function, which would be one polynomial divided by another polynomial. But basically, functions that are made up of polynomials and radicals and fractions are what I mean by algebraic functions. And then there's a different class of functions that we like to look at, which are those exponential functions. Maybe e to the x, 2 to the x. It'd be great to have another example in here where we're talking about something like 1/3 raised to the x power. That's another type of exponential function. Notice here, in a polynomial, the x is the base and there's a number for the exponent. An exponential function has a number for the base and a variable for the exponent. We also like to talk about logarithmic functions, those most common ones being the inverses of our exponential functions that I gave an example of here. So we might look at the natural log of x or a base 2 logarithm of x. And if we really wanted to, we could look at a logarithm based 1/3 of x. Whatever we could do with exponentials, we have to be able to undo them with logarithms. And then the last class of functions that we like to consider would be those 6 trigonometric functions: sine, cosine, secant, cosecant, tangent, and cotangent. Now, we also may occasionally consider the inverses of the trigonometric functions, and most of the time where you tend to lose people in a calculus class is when you rattle off those 6 trigonometric functions, and then you really lose people when you start talking about their inverses. We'll have a whole separate collection of videos where we do a nice review of trigonometry and inverse trig functions when those functions become of greater importance to us later. These are our 4 building blocks of any calculus class, these classes of functions. Now, what math teachers like to do, once you sit down and say 4 classes of functions, that's not so bad, I can deal with 4 classes of functions, we math teachers, we like to say, let's make things a little bit more interesting. Yes, we start with 4 basic classes of functions, the ones that I listed on the previous page, and then we like to build with them. We use them as building blocks, and our tools for combining them are tools like addition, subtraction, multiplication, division, and even function composition. So we take those classes or those families of functions and we start to combine different elements of different classes with each other via some combination of these operations. For example, natural log of the square root of the cosine of x, or we could look at something over here, a polynomial divided by the product of an exponential function and a trigonometric function. And that makes things a lot more interesting. And in order for us to study basically anything about hard, complicated functions like this, we need to stop, and before we do that, we need to study the behavior of each of these individual families of functions first, and then we need to figure out if there are rules for once we understand what's going on within a particular class. Say, for example, that we get really good at computing limits of polynomials, and we get really good at computing limits of exponentials. Then we start combining polynomials and exponentials together using these things, and we say, okay, is there anything I could say about the limit of this new combined function, given that I very much understand what's going on in the limit cases for each of the individual pieces. And we repeat that story with limits, with derivatives, with integrals, with all things calculus. So where we're going to start is by taking a look at each of those 4 classes of functions. We're going to look at the limits of those functions as x is going off towards infinity, and we're going to say, are there any rules for how we combine limits when we combine functions according to these operations? Why limits is a really good place to start is because limits behave. When we understand what's going on with the limits of these individual functions, and then we start combining them according to the operations listed previously, when I say limits behave, I mean the limits do what you might expect them to do, and that's a really helpful thing. So for example, if I have two different functions, as x is approaching something, if I happen to know the limit of f, and I happen to know the limit of g, as x is approaching a, and I combine f and g by either adding or subtracting those two functions, then the limit of the new function I've gotten from adding and subtracting is just equal to the limit of the individual functions either added or subtracted according to whatever I did over here. So the thing that you would want to be true about the limit of those functions is true. If I want to add two functions together and know the resulting limit, just add the two limits together. A similar thing happens when we either multiply or divide with limits. If I have two functions and I understand the limit of each of these functions as x is approaching some value, then if I were to multiply these two functions together and ask for the limit, it should just be equal to the limits multiplied together, a thing you think it might do. We have to be minorly careful with the quotient rule because remember there's a much higher governing law in mathematics, which is thou shalt not divide by 0. But if we're going to take two functions f and g and divide them and then ask for the limit as x is approaching this particular value, what we should get is the limit of the top function divided by the limit of the bottom function. And that will all be just fine and dandy unless the limit of the bottom function is 0. Because if the limit of the bottom function is 0, we know we aren't allowed to divide by 0, and then this theorem isn't going to try and break that rule. But otherwise, if it's anything other than 0 and you divide the functions, it's going to behave just the way you thought it would. And the only time it's going to give us trouble is when division gives us trouble more generally. A similar thing happens. These rules, there's something called the power rule, which is a little bit less used, but I'll present it here just for completeness. If we had a function and we understood its limit as x was approaching something, and then I wanted to take an nth power of that function and then ask about the limit, it's just going to end up being the nth root of the limit as long as I'm allowed to take nth roots. So when n is like a nice positive number, like a square or a cube or whatever, no problem. But if I'm trying to take square roots, remember that we can't take the square root of a negative number, or more generally, we can't take an even nth root of a negative number, and so we can only go so far as saying, well, yeah, and I'm allowed to take nth roots as well, as long as we know that the function has a positive limit. So just like with the quotient rule where we ran into trouble when we were trying to divide by 0, we know that dividing by 0 is bad. Over here, we know that taking square roots or nth roots of negative numbers in general can be problematic. So as long as we just stay away from negative numbers and we have positive numbers, then it's okay to take nth roots as well as powers to say that limits behave.